Hello guys and welcome to another video with Cass on the Mesma channel. Today we're going to take a look at solutions for the diagnostic pulse generator. So as always, let's start with the basic inverter solution. So it has a total cost of 3, uses 238 power and 5 lines of code. Okay, so by checking the information tab, it says that when the button is pushed, generate pulses as indicated in the verification tab until the button is released. So you can see that the board is very simple as well. So let's check the verification tab. So yeah, what you see here is basically they want us to output a wave pattern like this for as long as the button is pressed. So here you can see a long press, here is a little bit of a shorter press, and what the code does in this case, which is why I'm calling this the inverter, is it just moves the accumulator to the output at any time, and then it sleeps. But then it checks the button, and if the button is pressed, we use the NOT instruction to invert the value inside the accumulator. So next time it's going to be 100. If it's pressed, then it's going to sleep. Next time it's going to be 0, and then 100, and 0, and 100. So it will create this alternating pattern. As soon as the button is not pressed, we move 0 to the accumulator because we want to make sure that it resets. The reason is if we're holding it for a even number of time units, it's going to end up being 0 anyways, but otherwise it's going to be to end up being 100. So if we advance in here, we can see how the patterns are generated now. Yeah, so yeah, move 100, sleep, invert it, yeah. And that's it. That's it. So let's see what happens when the button is released. So it's released, it sleeps, and then yeah. So all the time we are executing 1, 2, 3, 4 instructions at all times. So yeah, this is how this works. Okay, so let's check other solutions. Okay, this next solution is something that used to work but doesn't anymore. So it uses gates only, so 0 lines of codes, guys. And the solution was actually not mine. I found it somewhere, maybe on Reddit. And yeah, it just uses logic gates. But since the game changed, they have no delay anymore, so this thing doesn't work at all. If you guys know how to make this work again, yeah, just hit me with a comment in the comment section. And next, I want to show you the gen using the gen instruction, which is the secret instruction. So spoiler alert, and I managed to solve this with only 3 lines of code. The cost is the same, but we use a lot less power. Check this out, guys, 140 and 42. Yeah. So here's the solution. So all the time we are checking if P0 equals 0. So checking if the button is pressed. And if it is, we use the gen instruction. So let's check the verification tab. And what this does is it goes high for a second and then low for a second. All right. And because it goes low for a second, it also works as they sleep. So we don't need to sleep because we have already slept from the gen instruction. So this is cool. So next cycle, if the button is still pressed, we keep doing this. So we create this pattern. There's no problem with resetting it because it will always go high and then low. It will never end as being low. And if the button is not pressed, we just sleep. So check this out, guys. We are sleeping most of the time, which is why this solution is power efficient. And here's how the gen is doing its thing. And yeah, pretty cool solution, huh? So, and finally, I have a really amazing solution that uses only 1 line of code, guys. But it's a little bit more expensive. So yeah, it costs 4. It's pretty decent in power usage and only 1 line of code. So let's see what this magic solution is. There it is, guys. The solution in all its glory. So this is a muxer, and yeah, there is a tutorial on my channel if you don't know how this works. But basically this will give out a value X. And the first digit of this value is going to be whatever comes from P0. If it's 0, it's going to be 0. And if it's a 100, it's going to be a 1. The second digit is going to be P1, and the third digit is going to be P3. So for instance, if we activate P2, our input is going to be like this. All right, and if we activate P1, what comes out of this is going to be 10, and if it's P0, it's going to be like this. So yeah, we want this thing, this gen instruction to be like this. If the button is activated, we want this configuration for the gen, right? So we go high and low, and then high and low and high and low. And if the button is not pressed, we want this to happen. So we never go high, but we go low for one time unit so that we sleep. So this works as sleep most of the time. When the button is pressed, this becomes this. And this variable is just x0, all right? And we have this component here because if we connect these directly, well, it's not possible in the first place, but even if we read from P0 down here, well, so it's possible, this would work like this. So it would become 100, so we would sleep for 100 cycles, which or go high for 100 cycles, which is definitely not what we want. So we just stick with this. All right, so this is a one-line solution. You can see that it tries to write 100 here for a second, then it kind of clears it. Here you can see the alternating pattern. So let's go back to not press the button, and then you see it goes to 100, but then it gets canceled immediately because it stays at 100 for 0 seconds or 0 time units. And this is just how the gen instruction works, which is why this instruction is a little bit power hungry as well. So yeah, very simple solution, very interesting solution. All right, maybe we could take a quick look at a more complicated and conceptual solution to end this video, because as you can see, this solution is way more expensive. The power consumption is way off the charts. Look here, 572. And then we also use 7 lines of code, which is like everything is worse with this solution because this is conceptual, and this is used in my video where I explain what micropulses are. So yeah, basically we have a complicated component here called a FPGA, where we can basically configure it by setting those little dots in here. And then in every cycle, if necessary, we send a micropulse in here, and this is configured to become a T flip-flop. All right, so then it activates the T flip-flop in every cycle. So it's not doing anything for now. So yeah, saving a little bit of power, and then it starts. So you can see that at one cycle it's going to be 0. At the next cycle it's going to be 100 because it is a T flip-flop. So we just send pulses to it. We send a micropulse, it becomes 100. We send another micropulse, it becomes 0. And this is pretty much like what the gen instruction does. All right, so yeah, I don't think it's going to be clear if you don't understand how FPGAs work. So make sure to check on my playlist where I have the tutorials and where I explain everything, all the concepts that I'm using on this series. That's going to be it, guys. Feedback is always appreciated. Thank you very much for watching. Can't wait to show you guys my next solutions. Bye.